Hello there, and welcome to Binomial Distributions, friends or foes, you decide. However, we are strictly going to be going over how to start off a binomial distribution. And when we talk about starting off a binomial distribution, we're going to talk about the equations. We're going to talk about some of the properties of a binomial distribution. So do not expect calculator functions in this video, but this will show you how to set up the functions for the calculator functions. So here we go. So binomial distributions are very finicky creatures because they have four specific requirements that we do have to adhere to. And number one is we need a certain amount of trials. And those trials we're going to refer to as n. We also need a probability of success for each of those trials, and that p of x or p, whichever we're going to prefer, which in this case is p, has to be a constant. So there has to be a certain amount of mutually exclusive outcomes. Now, when we talk about mutually exclusive, we're talking like pass-fail rates, success failure, married versus not married, two things that can never interact with each other at the same time. Also, we're looking for each part of the trial to be independent of each specific item. Whoops, forgot the L. So we have to have a certain amount of trials, successes, mutually exclusive outcomes, and we have to have independent trials. Now, as far as the formulas are concerned, there's multiple variations upon the formulas. Two of the most common ones we're going to show you here is the sum of the computational formula times the amount of successes times the amount of failures. Now, mind you, this P over here stands for the likelihood of success, while the Q, on the other hand, stands for the likelihood of failure. So the amount of successes versus the amount of failures and the combination between them. Or, if you prefer the other formula, which is most commonly found in our Pearson textbooks, we see the sum of the computations, pass rates, fail rates. And again, if you notice, the notation is very similar. It's just that last one that we have to deal with. So, combinations, pass rates, and fail rates. Or you can say amount of passes and fails, whichever you prefer. Just know that we're going to be dealing with an N, P, and Q. But, there's a but to this. We don't want to deal with R's all the time. We want to start dealing with X's, because when we start talking about our binomial requirements, we're referring to this R as successes, the amount of successes. So we're just going to start crossing them all out and referring to them all as X. Okay, everybody still with me? Perfect. Now the binomial formula will only account for any X amount of successes at one time. Now when we say X amount of successes, X can be anything from 0 to the amount of numbers that we have in our trial. So from 0 to N. Okay? If you're still with me, excellent. If not, rewind a little bit. We're going to go a little step further. The binomial formula will only allow for a discrete occurrences of events. So X cannot equal like 2/3 amount of successes. X cannot equal 1/10 amount of successes. N is going to be a whole number or an integer, and X is usually going to be a integer. Okay? As long as we got this, we've got no troubles. Now, as a refresher, if you don't know how to do the computational formula, the formula is going to be presented to you now as n factorial over x factorial times n minus x factorial. Mind you, this exclamation point we're referring to as a factorial. And we'll show you how to do factorial mathematics in just a minute. But if you want to use the NR formula, depending on your textbook, it's the same exact thing. Just replace the x's for r's. So when we're dealing with x's instead of r's, we're merely trying to appease those who want to use different versions of the textbook. So to do factorial mathematics, you're really multiplying each number as it goes down to 0. Now, for those of you who don't know that, we're going to do 5 factorial, which simplifies as follows. Now, wait a minute here. How the heck did this happen? Well, a factorial means you multiply all the way down. So if you have 5 factorial, you go 5 times 1 more down, 4 times 3, 1 more down, 2, 1 more down, 1, and you keep going down till you get 0 factorial. But since all of this is multiplication, we're going to try and simplify it first. So 5 times 4 is 20, 3 times 2 is 6, and wait a minute, 1 times 0 factorial is 1? How can that be? Wait a minute, 0 factorial is 1. That is a constant in mathematics. Don't worry about how to do it yet, because 99% of the time what you're really worried about is just doing this. Most textbooks won't even let you consider 0 factorial because they'll just go 5, 4, 3, 2, 1, 0. So once again, most of the time your textbooks will go 5, 4, 3, 2, 1, 0. But for those of you who have dealt with binomials before, 0 factorial is strictly 1. Okay? Everybody okay so far? Moving along. So let's give ourselves something to work with here. Let's say our n is 5, so we got 5 trials, and the likelihood of success is 0.5 for each of them. Well, there is a way to calculate an expected value, so it's the amount of occurrences that we expect to succeed. And the formula for it is n times p. Not a problem. 5 times 0.5, let's see, that's about 2.5. Wait a minute. We said that x has to be regular numbers like 1 or 2 or 3. Well, that's perfectly fine. The expected value can be any number, and it can be decimal values. That's not a problem. It just means that we should expect x to be around 2 or 3. Make sense? Good. And by the way, for those of you who aren't as familiar with it, we often refer to the expected value as the mean of the distribution. Okay? So when you're talking about standard deviation, or the standard deviation that you should know from earlier parts of your textbook, when dealing with proportion, the formulas look a little funky. Now, I'm not going to go over the proof and the equality as to why these work out. Just know that this is a formula for standard deviation, where Q is going to be the failure rate. So 5 times 0.5 times 0.5, put that under the square root. And what do we get here? Oh, let's see here. We should get roughly about 1.12. So when you're talking about expected value for a binomial distribution, we refer to it as mu. And if we're talking about standard deviations, we often refer to those as sigma, just like earlier on in your textbooks. Everybody good so far? Good. So now to set up our full binomial distribution. Now, just like before when we were calculating ungrouped standard deviations, we're going to set this up to look kind of like a table, where we're going to list out all our n's. Wait a minute, all of our n's. Let's see, we said n was equal to 5, and we can't change the number of trials that we have, so n's not going to change at all. It's just going to be 5 all the way through all our calculations. Now, when we're talking about p, let's see here. Well, p's got to be the same for everything, so we're just going to keep that the same. And if we're talking about the number of successes, hold on here a second. X is the number of successes, correct? Just like what we discussed earlier. Well, can we have 0 successes out of 5? Sure. Can we have 1 success out of 5? Not a problem. 2? Well, that's a little more likely. 3? Definitely. 4? Absolutely. But wait a minute. Can't we have, in 5 trials, 5 successes? Yes, you can. So let's set up our table a little more appropriately, shall we? 5 trials, 0.5 success, 5 successes. And if we pull out our binomial formula from earlier, I'm just going to pick one of the two that we used, then we can set up each of the corresponding rows so that way we can find the likelihood of success using binomials. Alrighty. So let's see here. Now mind you, Q is still the failure rate. So we got 5 with 0 successes, P to the 0, Q to the 5. Okay, not a problem. You proceed down the rest of your math accordingly. Notice how we have the 0 increasing each time by 1. And we have the P increasing by 1 because the amount of successes is increasing. And we have the failure decreasing because if we have a certain amount of successes, then we should also have a certain amount of failures. Another thing you should also notice is that 0 plus 5 still all adds up to 5. And the same thing here, 2 to 3, 1 to 4, 3 to 2, 4 to 1, 5 to 0. So there's a lot of patterns that you can distinguish here, but you should know that this is always increasing by 1. And you should know that the other side is decreasing by 1. Everybody still with me? Now, again, this is if you were to write out an entire binomial distribution by hand. So let's see what our answers are going to come out to. So if I have 5 successes and I choose 0, there's a 0.03125 chance of success. Well, if I have 5 trials with 1 success, about 15%, 5 trials, 2 successes, 31%, 5 trials and 3 successes, 25%. Wait a minute. 5, 0 leads up to 3. 5, 1 leads up to 15. 5, 2 leads up to 31. And 5, 3 leads up to 31. Holy crackers. Where have we seen something like this before? This looks an awful lot like a problem we did earlier involving flipping coins. Oh, so how is this useful? This is a table that involves the likelihood, which we're going to call P of X, of flipping a heads. So out of 5 coins, 0 heads. 5 coins, 1 head. 5 coins, 2 heads. 5 coins, 3 heads. Ha ha! Let's continue on with the rest of this. Now, even though these two values are the same, don't be fooled. It's just another way to trick you. So 15% and another 3%. Now, is this graph always going to come out symmetric? Not really. But if you do notice that there is a clear divide down the middle of this graph, which corresponds to our mean of 2.5. Oh, another property here. So there should be a clear divide in the likelihoods somewhere around the mean. Now, as far as the rest of this is concerned, I wouldn't be too worried about it. But we're going to use this table later on to help us establish the probability distributions in terms of let's say 0 to 2 successes, or 0 to 5 successes, etc., etc. Everyone still with me? Well, we're approaching the end of this video, but one of the last things that I want everybody to know is that the sum of all the values in the last column, so the binomial column, is 1. So if you add up all those values together, you should have gotten 1. And there is plenty of time, now that you're at the end of this video, to go back and check my work. It is true, though. This is the tall guy signing off, and enjoy. And remember, this was just to show you how to set up your binomial probabilities. So you can use this in every single case of binomials. Keep in mind, this gets really cumbersome when your n is bigger than 10. Otherwise, you're going to have to keep writing out table after table after table, and it gets old really quickly. Another thing you want to watch out for is to make sure that your p is always equal to some number, which means your q is going to be equal to 1 minus p. And finally, there should be x number of successes. All right, everybody. Once again, this is the tall guy signing off.